Great. I think we are going to make a soft start while the troops make their way back. Hi, I'm Hamad Haddadi from Imperial College London and Brave Software. I'll be chairing the next session on testing and verification of networks, which is quite important as the networks get more crazy. And we got 5 solid, well-executed papers in this session. First one, we got Flash, fast, consistent data plane verification for large-scale network settings. The presenter is Ying Zhang, who is a senior engineering manager at Meta. She works on large-scale network planning and network management problems. Her team owns software for network modeling, planning, simulations for a Meta data center, and backbone and edge networks. Her research interests are in large-scale network management, network for AI, software-defined networks, and network functionality virtualization and routing. And they are looking for interns and hires, so do catch her later on. Over to you. Thank you.
Thank you. Thanks for the introduction. Hello, everyone. My name is Ying. I'm going to give the talk today about Flash, fast, consistent data plane verification for large-scale network settings. I'm giving the talk on behalf of all my co-authors. Unfortunately, they cannot make it here in person, so here I am. So this paper is about data plane verification. And data plane verification, we all know, is a very important primitive for the network reliability. At the high level, a data plane verification system collects FIB routing forwarding information base from all the switches and routers and to collect their updates. And at the same time, they take the input as the network-wide requirement. Then they check against the requirement from the FIB and generate the results. So in order to perform this verification, a typical way is that from the FIB and the FIB update, we create a network model. And then we develop a requirement checker that checks whether the requirement is satisfied on this network model and generate the results. So there are typically in the previous work, there are rule-based model creation and requirement checker, such as HSA and NetPlumber. In order to increase its scalability and performance, people have looked at different optimization methods, such as equivalence class. This is a very well-known approach. Equivalence classes essentially captures the header spaces where all the packets share the same forwarding behavior. So you can create a forwarding graph and then perform the checks on this graph. However, in this work, we found that there are kind of 2 gaps in all of the existing data plane verification tools. The first one is that none of them can handle very fast updates. We call it update storms. So basically, this is a large number of data plane updates that arrive in a short time. So and this is very common in typical production. Let's say in a data center, we have a new pod with K-array fat tree topology, and each pod has P prefixes. Then we can easily compute the number of updates can grow to hundreds of thousands as this K number and the P number increases. And existing work, for example, APKeep and DeltaNet, they are designed to process a single update each time. Therefore, they cannot keep up with the update storms. The other gap we found is that some updates, they also arrive too slowly. For example, it takes a long time to collect all the updates from all the devices. And this can happen because of a number of reasons, such as FIB computation crashes in the middle, insufficient computation resources. There can be dampened FIB computation due to unstable links, so the update did not get sent in time. And it can be also due to network problems, such as incast congestion. So existing work, latest work, APKeep, DeltaNet, they either wait for all the updates to arrive, so the verification results end up being generated with a much longer delay, or they proceed with a transient and potentially inconsistent data plane and then generate false results. So here it comes with the high-level idea of Flash to address these 2 problems. at a very high level, the idea is pretty straightforward. To handle update storms, we want to process a block of updates instead of a single update each time. And to handle long-tail arrivals, we want to be able to verify, even without the complete set of the data, with the incomplete data plane states. So the idea is straightforward, but really realizing it to handle all the corner cases in real world is not easy. So next, I want to walk you through a few challenges to illustrate why it is not easy. So one simple idea to process a block of update is that we could aggregate root updates. But naively aggregate them may cause inaccuracy. So to give you one example, this is also a running example we use in the remainder of the talk. So we have a data plane of an IPv4 network. Let's say each switch has 2 routes to start with. And this is our longest prefix matching. So the more specific prefix rules gets preferred. So if we build a network model and create equivalence classes, we can easily see for these specific FIB entry, we have 2 equivalence classes. Now we receive the FIB update, delta R, with 3 rules. And to manually craft the composition, the correct composition, we will prefer the more specific prefixes rule first, so that the equivalence class, the header space, gets carved out to smaller pieces. And at the end, the correct composition is that it will end up with 5 equivalent classes, as shown here at the very bottom. So how do we achieve that? So one idea is that if we look at the update, we can see some updates have similar actions. Can we group them together? So let's try to group these 2 updates into one. Since /3 is covered by /1, so we can kind of merge these 2 together and reduce to be the new delta R. However, if we look at this composition, by composing R and delta R together, this will lead to inaccurate results. So this is because when we do this merging, we actually ignore the higher preference rules here in A1. Because /2 has a higher preference than /1 rule, and when we do this merging, it gets ignored. So that's why it leads to an inaccurate number of equivalence classes here. Then the second idea is that can we aggregate models? So we apply rules to our current model one by one, and then we look at if we could just aggregate the models directly. It turns out it's also not that trivial. So in the same example, we apply every single rule in delta R with the original FIB, and then come up with these 3 different model updates. And if we want to combine the last delta M2 and delta M3 because they share the same action, then we may end up with delta M23. However, this is also not correct. The reason is because delta M1 and delta M2, they're not conflict-free. P4 and P3, they actually have overlap. So if we blindly just combine either models or rules without considering the potential overlapping between predicates, and this can often lead to inaccurate answer. Then let's also coming back to the other part of the problem. The updates, they come with a much longer delay. Then how do we do the verification with incomplete data plane state? So in this example, we have a network of 3 switches, and each has the forwarding rule as below. And according to the forwarding rule, we can easily construct a forwarding equivalence graph like this. Now, if we observe an event of a link down between S1 and S3, So as long as S3 updates fib before S2, in reality, there is no loop. However, it may not be always the case from the verifier perspective. Let's say if the update from S3 arrives later than the update from S2, then the verifier will falsely raise an alert of the loop, but in reality, it didn't exist. Similarly, we could also be caught in a transient state. The same example of a network of 4 switches. In this case, we're looking at the 2 links are down. So when there are 2 links down, it could be there is a transient state that S2 says that the packet should be forwarded to S4, and S4 says the same, and there is a transient loop. So in this case, verification captures it, but raising too many alarms for transient state sometimes can be very noisy, and it's not very useful in real-time operation. So we also want to avoid raising too many of these transient state alerts. So let me go into our proposal, FLASH, fast, consistent data plane verification for large-scale network settings. So at a high level, we augment each switch with an agent, and this agent will monitor the fib update and its current network state. It will tag the fib update with its associated network state and send it to an update dispatcher. The dispatcher will group the updates into update blocks according to their tags, and then each block will be used to update the corresponding network model. We also develop an incremental requirement checker that checks the requirement against the model delta and generate the results in a more efficient way. So there are 2 main approaches that we propose here. The first is how do we update the model fast with any update blocks. The second innovation here is a consistent, efficient early detection mechanism. So next, let me first go to fast IMT, fast inverse model transformation. So our key observation here is that processing updates sequentially will incur redundant and unnecessary computation. So then the natural idea is that we should identify the computation that can be aggregated. But it is not very easy. And the key idea is to decompose naive updates into a set of composable atomic updates. So these are the key ideas of fast IMT. Again, I'm going to talk about it using an example. So the same example of a fib with 2 entries to start with, and then we receive the fib update with 3 data rules. So the first core idea is that we need to identify the fib updates that could be potentially aggregated. So we call these candidates expanding rules. Expanding rules means that these rules, they could cause an expansion of the original header space and action space. So in this example, the 3 expanding rules are marked as yellow. The next step is that we need to compute a set of conflict-free updates from the expanding rules. So conflict-free, we call it conflict-free overrides because they do not overlap with each other. So in this example, P4, predicate P4 and action A3 is a conflict-free overrides because there is no other rule that goes over its priority and has a different action. The conflict-free overrides are order independent so that it allows composition. For example, we can aggregate by action so that for this switch, we ended up with two rules by composing the last 2 actions that has the same A4 action together. And that was just for one switch. And if we look at all the switches in the network, we can also aggregate by predicates. Then we end up with a delta M. So this is really the model update we use to update our final model. And after applying to the model, we can get a new equivalence class and the actions mapped to each equivalence class. In terms of implementation, this model update process is actually pretty computational expensive, so we leverage distributed compute to speed it up. We also have a lot of optimization in terms of efficient data structures for prefix rules and persistent action trees. Please refer to the paper to see the details. The second idea is consistent, efficient early detection. So again, here the observation is that network errors can be identified without collecting complete data plane. One example is loop. When loop happens, as long as we collect all the updates from the switches that are involved in the loop, then we can declare a loop. Right? As long as these switches send us all their updates, we don't necessarily need to have the updates from other irrelevant switches in the network. So that leads to our key idea to perform early detection on a consistent network state. So the core idea is to construct models for consistent data plane states. So in this example, we look at two events, S1, S2 down, and S1, S3 down, and we illustrate them using a timeline. So for each of these events, by the time it happens, all the updates it triggered arrived in the verifier. That is the time we say the data plane is consistent, and we can perform a verification. So in order to do that, we use a trick to define synchronized node. So each node, upon a network state change, it will generate a bunch of updates. So the node, each switch or each agent on the switch is responsible for batching all these updates together and sending to the verifier and tell the verifier, I'm done with sending you all the updates I have for this specific network state. And by the time the verifier knows that this node is synchronized and mark it as synchronized. And this is a very important concept we use to decide which node is ready for early verification, which node is not. So in this example, all these three are consistent models. They just happen across time. And whenever the model is consistent, we can perform verification on this model. Just to further illustrate how the consistent model are constructed, so each agent tags the root update with its associated network states. So in this example, we have 3 network states, and they are marked as 3 different colors. And each agent, their updates are marked as different shape. And they send all the updates through the dispatcher. The dispatcher put them in different epoch. Then the consistent model will check if any node is synchronized. If it is synchronized, then it processes the update and mark this node is synchronized. And how do we use this to actually check the requirement? The key idea is that we also use regular expression, like many other papers, to check requirements, such as reachability loop waypoint. And our incremental reachability query is performed on a decremental verification graphs. So in this example, suppose we want to check that for a particular destination 10/8, S must follow this specific path, either go through W or Y, and then end it at D. So throughout the time, we receive different updates. Let's say we first receive this update, and S and A are synchronized. So we're ready to check that. So this means that in the verification graph, there is a portion of graph that we know it's possible to traverse. Then next, we receive another update with more information. Now AB, BE, EC, they are all synchronized, they're converged. So then we can further zoom in into this node to to basically limit the verification graph to be a small portion. And at this point, we can already raise the alarm that the requirement is violated. Okay. So we perform evaluations on 3 large networks and using real data center topologies. We also test on open source software as our agent. And I want to quickly show you some of these evaluation results. We compare against the 2 latest work, APKIP and DeltaNet. And from these, to test about update storms. So overall, the existing work cannot finish over 10 hours, but our work can finish within 19 and 4 seconds. So this is a 9,000 speed up. We also test the ability to do consistent detection. And here we compare with 2 mechanisms based on a single update and based on a block of updates. So here you can see that the 2 previous methods will still report transient errors, versus our method is pretty consistent and only a significantly reduced error reported. And lastly, about the time of early detection. So it also shows very promising results. So detection loops within is smaller than 153 milliseconds, which is 390 times faster than the baseline. And we also tested on Internet 2 dataset, which is 79 times speed up. So to conclude, today, I present Flash. It is a fast and scalable data plane verification system that addresses really 2 issues for practical data plane verification: update storms and long-tail arrivals. And we contribute 2 new areas to solve these 2 problems. Thanks, and I take questions.
Okay, I don't think my microphone is enabled, so I have to come in an awkward way close to you. We have time for 1 question while we switch over. If you have a question, now's your time. Introduce yourself, ask your 1 question. I think, are you ready to ask, or anybody? Because we are massively over time. Don't be shy. If you have that 1 burning question, now's your chance, which is what I ask, because we are massively over time while we switch over to the next talk. So what happens in case of overhead rewrites and in the bad scenarios? What's the overhead of, as in when we have rewrites of the, I think that was one of the points that was brought up. But maybe it's better if I ask it on Slack.
Yeah, sure.
Okay, great. Okay, let's thank the speaker 1 more time. Thank you very much.
Thank you.
Right. Thanks.